So today I want to talk about geometric series. Now we talked in a previous video about arithmetic series, and those were series that were basically sums like 2 plus 5 plus 8 plus 11 plus 14, where between each of the two terms there's a common difference, right? You're adding 3 each time, if I did this right. So this is arithmetic series. And we derived a sort of a formula that allowed you to add up an arithmetic series really quickly, which basically involved looking at the fact that the sum of the first and the last term, 16, is the same as the sum of the second term and the second last term, 16, and sort of generalizing that to get a formula. Now looking at geometric series, it's very similar, except you're adding up terms, except now the difference between each successive term, it's not that it's a common difference each time adding 3, it's that it's a common ratio. So in this case, we can do each time multiplying by 3. So then this would become 18, because that's 6 times 3, and this would become 18 times 3, so that's 54, right? Check my work, 18 times 3 is 54. Times 3 again would be 112. Okay, and hopefully I don't rewatch this video and realize I made some kind of basic multiplication mistake, although that would be very like me. So here we have an example of a geometric series, because you're adding up a bunch of things, and between any two of them there's a common ratio, right? Multiplying by 3 rather than a common difference. And maybe it's worth looking at another kind of geometric series where the common ratio is a fraction. That's possible too. So we could imagine starting out with, let's say, half, and then adding to that a quarter, and then adding to that an eighth, and adding to that a 16th, and so on. And here, the number we're starting out with is a half, and in fact the common ratio is also a half. To get each next term, we multiply the previous term by a half. So these are geometric series, and they come up all the time in practice, and we'll see in future videos lots of cases where they come up naturally. And what we want is a way of quickly adding up a sum of terms that have this pattern to them, where each term is some multiple of the last term, and that multiple is the same as you go through. How can we do that? So let me give myself some space. And let me start by writing down a general geometric series, which will look like this. A stands for the first term, which is sort of free choice. Now the second term is going to be A times R, because I always have to get the next term by multiplying by some number, and here I'm going to treat R, that's going to be my common ratio. So then the next term should be the previous term times r again, so that's ar squared plus ar cubed, and that goes up until some ending point, so we'll say plus ar to the n. And actually, because over here we can think of this as like ar to the 0, to sort of, this is ar to the 1, 0, 1, 2, 3. I'm going to make this go up to ar to the n minus 1, because then I can say that this entire sum has n terms. Okay? So how can we figure out a formula for adding all of these terms up in some kind of clever or fast way? And here's the idea. Let's call this sum S sub n. So S sub n stands for the sum of these n terms of this geometric series with first term A, or A times 1, first term A, and common ratio R. And here's what we can observe. If I take S sub n and I multiply it by R, that's going to equal R times A plus AR plus AR, squared plus AR to the n minus 1. So I'm just saying, what if I multiply the entire sum, whatever it is, S sub n? The entire sum, what if I multiply it by r? Well, I can distribute it through and I get AR plus AR squared plus AR cubed all the way up to AR to the n. Each term gets multiplied by r, so each term essentially shifts forward. And where in the last term we get AR to the n, because when it's multiplied by r, it becomes a term that wasn't in the previous sum. And the reason this ends up being a clever thing to do is because this new sum, which is the old sum times r, overlaps a lot with the original sum, right? AR is in both, AR squared is in both, AR cubed is in both, AR to the n minus 1 is in both. The only places they don't overlap is that this sum down here has an AR to the n, and this sum up here has an A without an R, or an AR to the 0. So what we can do is, I don't know which way is better. So let's consider Sn minus R times Sn. Because they overlap a lot, if I subtract them, there should be a lot of cancellation, right? Sn is this entire sum, so I'm going to write the A part of that. And then when I subtract this sum, all of these terms are going to cancel, and all that's going to be left in the subtraction is AR to the n. And now maybe you can see why this is going to be so useful, because by rearranging this equation, this is an equation between, on the one hand I have A minus AR to the n just by figuring out the subtraction, but on the left-hand side here, I have Sn. It's not isolated yet, but that's the thing I wanted to figure out. Sn is the very sum. Sn is the question mark. So I can rewrite this as Sn times 1 minus r by factoring out the Sn equals A minus AR to the n. And then I can solve, provided that I'm not dividing by 0 here, I can solve Sn equals A minus AR to the n divided by 1 minus r. Now that only works, that only works if r is not equal to 1. If r is equal to 1, then I have a problem because I just subtracted the same thing from itself because r was equal to 1, and then I just have 0 equals 0, and that doesn't help me. But on the other hand, if r equals 1, then this whole sum here is just a plus a plus a plus a plus a, and that's just an arithmetic series with common difference 0, so that's sort of already taken care of. So we might as well assume that r is not equal to 1, in which case I'm not dividing by 0, in which case I figured out a formula for the sum of the first n terms.